Hi, welcome to the second video in this series. In this video, I'm going to go through two examples, showing you a flood dose example and an elevated sand mound example. And just to recap from the last video, let me pull up the PowerPoint here. I've created 3 spreadsheets in St. Joseph County, and these spreadsheets utilize the operating point method to analyze a pump's performance, to take the operating point and then apply it to check for code compliance throughout all of the code checks that are required. For an elevated sand mound, it goes through 14 checks. For a flood dose system, it goes through 5 checks. And then it also does some general engineering checks. And that's based on the different, there's more checks for the sand mound and pressure trench and less for the flood dose. But it also offers recommendations if the design does not meet code compliance. And like I said, in St. Joe County, we're starting to require that every pump design is checked with this spreadsheet. It saves us time. It just takes 2 to 3 minutes, 2 to 4 minutes to actually input all the data, and then it automatically analyzes everything for us precisely. So there's a lot of power to it, and we're also going to encourage people to distribute to their contractors. It's not a design tool. I just want to clarify that. This is a checking tool, and the hold harmless agreement at the beginning of the spreadsheets talk about that and talk about this is only for checking. This is not for designing. So let's take a look at the various spreadsheets that I have. As you can see here, there's a flood dose, pressure trench, and sand mound. So let's start off with a flood dose spreadsheet. I have here a design that was submitted, and this actually was analyzed in the previous video. I just flashed it up as a screen that showed the input, but we're going to actually walk through the input. And remember, like I said, the first work tab, the worksheet tab down at the bottom, is the Read Me First tab, and that's the one we want to, it opens up first when you open up this spreadsheet. Okay, there's the St. Joseph County logo. There's a hold harmless agreement, so you read through this. If you agree to it, then you put your name. Okay, so I put my name, hit enter. Okay, it says you can go to the design check worksheet, which is this right here. But there's brief instructions here, and I added this to the first sheet because if you read these brief instructions, you're able to input the data on the next page. So I want to go through each one of these briefly. Okay, the hold harmless agreement must be accepted to use a spreadsheet. If it's not, you can see here that you get some big flashing red things on the next page. So you have to accept that. So let's just do my initials. And those flashing red things go away. So the next instruction is that all cells in tan coloring must be filled out for the spreadsheet to perform correctly. This is important. This is why the 2 tabs at the bottom are colored tan. And so here's all the tan colored cells. Notice that other cells on the worksheet, if I click on another one, it won't let me modify it. Same goes here. Any one like that. I have unlocked all of the tan color cells, and I have locked all of the other cells. So without the password, no one can really touch them. I want to re-emphasize here that you really need to fill out every yellow cell except for a couple. The property address and permit number, that's not pertinent to the actual engineering. And the other ones you don't have to fill out all of them for are the fitting table. You can just fill out some or you can fill out none, but they're colored tan to remind you that you can input data there. Okay, I made that point. This spreadsheet should only be used to check a previously designed single dosing pump. So, like I said, this spreadsheet is not a design tool. We recommend that you actually talk to your pump manufacturer because they will design and size your pumps for free. So you just give them what your system parameters, your elevation head, and the flow rates that you want, and they'll give you a pump. They'll size it for you. But this spreadsheet we want to be used only for checking purposes. So this is for the county regulators, possibly state regulators if they want to use it, and it's for contractors to see if their design meets state code compliance. Because even though a manufacturer such as Zoller, Barnes, AWeb, McDonald's, those types of guys, they'll give you a pump, but they're not going to check to make sure everything meets state code requirements. So that's when a contractor designer can use this. Okay, another great feature is that the item numbers listed on the design check worksheet, which is this worksheet. This is really the main worksheet that we'll spend time on. The item numbers on that worksheet correspond to the item numbers in the help worksheet. So if you go to the design check worksheet, you'll see these numbers off to the side, 1, 2, etc. And those all correspond with the help page. Here's the help page. Item 1 is a detailed explanation by item number. Item 2, all the items in there. Items 3, and then all the ones down at the bottom. All the checks are listed in here and explained in great detail. So that's great. And then here's just a general tip. Okay, so after I've put my name and accepted the hold harmless agreement, then I can go and proceed to the design check tab. I can put the property address, and it's Emmaus Road for all you Bible scholars out there. Okay, and then this, let me just emphasize again, this property address and permit number prints at the top of every page. So if you want to print this worksheet, you can see up at the top, there's the property address, and then you go to the next page and it prints up at the top there. So you can, just a nice little feature of the spreadsheet. Okay, number 1, it wants you to select the pump. So you look at what the contractor submitted to you, and you'll see that this particular contractor chose a Zoller pump. So I go to this drop-down arrow, and I can select from 4 different pumps. Now, just to specify and clarify here, I only chose the 4 pumps that we use mainly in St. Joseph County. I shouldn't say the county uses it. It's what the designers submit to us are usually only these 4 pumps. There are many other pump manufacturers, and I would recommend going to the Sump and Sewage Pump Manufacturers Association to look at the different manufacturers. Where there are more options, there's better designs. So I would like eventually to add more pumps to this list. However, it took a lot of time just to add these to the list. So this is where we are now. If we release another version, it'll have more pumps for sure. Okay, so Zoller. And once you select Zoller, you'll get the model numbers that pop up. And here are the model numbers that are for effluent and sewage pumps. So this particular contractor chose a model 98. Now let's say that a contractor chose a pump that's not on this list. Well, then you would simply select Other, and then go over here and also select Other, because as this says, both of them need to say Other. And then this table pops up, and it shows you, it asks for everything in the tan coloring that you need to fill out for the pump information. And it explains down here exactly how to enter this information. So we would enter from the 0 flow rate up to the max flow rate, and from the highest head down to the least head. And I also want to re-emphasize here, it has to have all 7 data points, and this is explained in the spreadsheet. I also want to say, make note that you need to put in the max head and the max flow rate, because this spreadsheet, the way that the engine of the spreadsheet works is that it will not give you an operating point that is above the max head or above the max flow rate. So you have to put those values in. Okay, but going back to here, let's get back to our example. He picked a Zoller 98. And see how easy it is to select other pumps? Okay, when I have a Zoller 98, you can see that on the chart that it plots the pump curve, pump performance curve, and the R² value, as I mentioned in the previous video, is very close to 1, so it's a very good fit. And so I can say, hey, it's not wavy, it's a very good fit. And again, as I said in the previous video, I recommend that you also check with the manufacturer's current pump performance curve that they've published. These can change over time. They probably don't change often, but they do change over time. So if you're watching this video and using this spreadsheet 10 years after it was created, I would highly recommend that you check every pump performance curve. Okay, the contractor initially chose a 3-inch force main. They had a horizontal length of force main of 40 foot, and the horizontal length is from the dose tank to the distribution box, so that was 40 foot. A vertical length of force main. A lot of people ask me what this is, and the vertical length of force main, if you're curious, all you have to do is go to the Help tab, and let's see, I was scrolled down to the bottom before. Okay, I go to item 2, and then it says here, vertical length of force main. So this is the vertical distance that the effluent has to travel. So see examples to the right. And I scroll over here. Here's some examples. So in purple, or some purplish color, it shows here that the vertical distance, as you can see, is 5 foot. It goes up 4 foot and then down 1 foot. Over here in this example, the vertical distance is 4 foot, 1 foot, very similar. It explains here that if you really want to be precise, you can account for the vertical height that it goes here and the vertical height in this hypotenuse. The vertical height that is created from the hypotenuse of that angled pipe. Here you can see that the vertical height is only about 4 foot because this is exaggerated. It's really just a few inches. It could be 4 foot and a few inches. Over here, the vertical height is 5 foot. So you can see that these detailed examples really help explain what it's looking for. Okay, so in this case, the effluent traveled 4.3 feet vertically. The pump off elevation, this is where the off float triggers. And some contractors may not give you an elevation that's real world coordinates. A lot of people in the residential industry will say some random benchmark is 100. Some people may not give elevations, but everything can be calculated relative to a datum. So for example, the bottom of the dose tank, you know that the off elevation is 2 foot from the bottom, so then your off elevation is 2 foot. So in this one, the contractor actually gave an elevation. So I'm just inputting these values. The pump on elevation is when the pump goes on. Pretty self-explanatory. Again, you can use a datum. So a reference point, a 0 reference point, and reference everything from that. It's however you want. Top of the pump elevation. This is what the software the spreadsheets use to check to make sure that the pump is always submerged. We are dealing with submersible pumps. Submersible pumps mean that the pump needs the effluent around it to cool the pump down. If it doesn't have the effluent, then the motor could burn out. It would definitely decrease the longevity of the pump, if not, burn it out. So here the top of pump elevation was 94.00. So top of pump would be from the bottom of the dose tank, and then and then if there's a pump pedestal, plus the height of the pump. So usually contract designers can submit that, and maybe your county will say, we require that you submit the St. Joe County pump spreadsheet to us for any pump design, and then the contractor would have to specify it on the spreadsheet. You can do it however you want. So the highest elevation of the force main, okay, what is that? That sounds kind of weird. The highest elevation of the force main, let's go to the Help tab. It's the highest elevation the force main experiences. It could be the distribution box or high point between the dosing pump and distribution box. So in this example, the highest elevation the force main sees is the distribution box. Here, the highest elevation is within the dose tank, and I've seen that before. So those examples help clarify. Where does the force main drain after each dose? You click on this drop down arrow, and we have several options. If there's a weep hole installed in the dose tank, then it'll drain back to the dose tank. And if the force main geometry forces it that way. Sometimes there can be peaks in the force main geometry, and only what drains into the dose tank, only from the peak to the dose tank will actually drain into the dose tank. You can say that it all drains to the soil field. Here's an example of how it all drains into the soil field right here, and I specify that right here. It says drains to the soil field. So there are many different options. Doesn't drain is an option. If you select doesn't drain, then it asks you what county will it be built in, and here's a handy dandy list of counties in case you're curious, and then it asks for the depth of force main beneath ground, and you can look in the Help tab for what that means, but we're going to select here it doesn't drain, or it does drain to the dose tank. Okay, we're going to fill out some fitting tables. This contractor likes to submit his fittings as basically custom fittings. They're not custom fittings, but the equivalent lengths are not found in the Indiana State Code fitting table. And so he specifies, he says, I have a check valve of an equivalent length of 17.2. And he says that he had a couple of 90-degree elbows with an inside radius of 4. And then he had a couple of others. You can see when I type in other that these cells over here pop up and appear tan, telling you to check that. Actually telling you to input data there. And so I'm filling out his fitting table. If your contractors are not giving you a fitting table, just ask them for that. That's just standard design. And it helps contractors too, because it helps them know what they're going to have to order before they actually, this is an interesting situation here, because he has a pump, this $1.98 pump, that has a discharge. It appears to me to be a 1.5 inch discharge size, and so then he puts an adapter to a 2 inch, and then his 2 inch goes to a 3 inch pipe, which is where he's getting his 3 inch force main. So that's what all these fittings are, and he wanted to have a custom, he wanted to use a custom 2 inch 90 degree, because this 90 degree corresponds with a 3 inch force main. Let me clarify that a little more. This fitting table will look up everything that's in state code. Right here, all these fittings that are listed in this drop down box, those are all part of the state code table. And when you select one of those, what it'll do, the spreadsheet will take that fitting and it'll apply the force main size to that fitting. And then it'll find on the state code what the equivalent length is, and it'll automatically do that behind the scenes for you. So if you want to do something that's not the force main size, then you select other and you put in the equivalent length. And you can see that, and we also need to put in here the quantity. Okay, so his total equivalent length of straight pipe due to fitting friction loss is 95.4. So that's kind of a mouthful. What that means is all the fittings in a force main system generate friction. Whenever fluid goes into a fitting and has to make that turn, there's more friction created. The Hazen-Williams equation has a procedure that you can basically say a check valve is, as shown here, 11.1 feet of length. It adds that into the total length of pipe as a way to account for friction. So you're not saying that you have an extra 95 foot of actual pipe. You're saying you have a extra 95 foot of pipe that goes into the friction equation to add to the amount of friction to account for the friction. So that's a little explanation of that. Plus, the help tab explains this in much more detail. Okay, describe the dosing tank geometry. Here I have many options. There's average gallons per inch, average gallon per foot. If it's a circular tank, then you put the diameter in. If it's a rectangular tank, you put the foot and the length and width. If it's other, you put a square footage, and it'll apply that over the pump on and off elevations. So here, the contractor submitted gallons per inch, and he had 33.88. So we put that into the spreadsheet. And some people may not be used to getting these values. If these values are not obtained, the dosing tank geometry, average gallons per inch, gallons per foot, that size, then you really can't check to make sure that the actual volume, the correct volume is being dosed. So this is important to look for. If your county is not used to obtaining that information, then it's something to get acquainted with for sure. How many bedrooms does a pump serve? 1 up to 6, and this is the way state code requires it. But you can also enter a user-defined daily design flow. And then this pops up to the right, and you can put in a value. Oops, that's a number. Here you go. You can put in a number. That'd be a lot of gallons. So for this example, it was a 4-bedroom house. Okay, so we go down, and this should look familiar from the first video. As I said, it automatically analyzes your system, and you can see here that it's operating at a very poor placement on the pump performance curve. So we see here that it doesn't meet the check number 8, the flow rate. And as I talked about in the first video, I saw, well, this system curve is really flat. Really what he should be doing is using like a 2-inch force main. So if we switch it to a 2-inch line, then we wouldn't need a 2-inch adapter here. So we can delete that. And okay, so then look at that, it automatically analyzes right away, instantly, the actual operating point, and it goes through and checks all for state code requirements. Look at how good everything looks now. We see all greens, but we see a C tips. The effluent velocity is 5 feet per second, and it says over here on the tips, verify that the pipe and fittings can handle velocity greater than 5 feet per second. And this is something that we can look at on the help page. Scroll down to item number 9, and we can read this and but I'll basically explain this. Essentially, pump manufacturers, a lot of them, not pump manufacturers, pressurized PVC pipe manufacturers specify on their website, several of them, that the maximum velocity in their pipes should be 5 feet per second. And the reason for doing that is basically because of water hammer. If you have a highly pressurized pipe and then you instantly shut off flow to it, it creates what's called water hammer throughout the pipe, where it shakes. We see it shaking, but really what it's doing is sending lots of pressure surges through the pipe. And those pressure surges can actually burst the pipe. And so when you have high velocities and they shut off real quick and high pressures, then you need to make sure that your pipe doesn't explode from water hammer. However, in these applications of simple flood dose systems or elevated sand mound systems, pressure trench, that we operate at pressures less than 20 psi, which is much, much, much less than what the pipes are made to operate at. And so if you were to shut off the flow from 5 feet per second to 0, the pressure surge has a much smaller impact on the pipe. So long story short, what we're saying is, as explained here in the spreadsheet, that the velocities greater than 8 feet per second should not be allowed. But if it's between 5 to 8, then you're probably okay. Just make sure you have pressure-rated pipe and pressure-rated fittings. So, okay. So I'm going to call that okay. And again, this checks for the right daily design flow and the right dose volume. And what this does is it takes the daily design flow, in this case it's 600 gallons, 150 times 4, and then it adds the drain back volume. So it says over here the required dose, which is, this is what you should have based on the length of force main and the size of the force main, the volume that's in there. You should be dosing 607 gallons each time. And it shows you how much they're dosing based on the dose tank geometry and the pump on and off, and the spreadsheet calculates it saying, hey, you're actually dosing 614 gallons, and that's really close. This isn't rocket science, so it's saying that that's probably okay. And as I described in the first video, this shows that it operates at a pretty decent location. If you're curious how the fare, why do I say fare? Go to the help tab. So help tab, item 12. How do I get fare? As you can see here, here's the middle of the pump performance curve. I'm calling a good portion, a good placement is in the middle 40%. A fair placement is between 40 and 66%. Poor, 66 and 90. And redesign 90 to 100%. So meaning if you're in the middle 40%, if you're in the middle 66%, you're probably going to be okay. It's a good design. If you're outside of that, then it's a poor design and you really need to consider redesigning this. And again, this is an engineering check. It's not a code requirement, but it's typical engineering practice. Okay. So that's an example of a flood dose system. Let us go to an elevated sand mound system. And I am going to breeze through some of the initial explanations I gave for that last spreadsheet and just go straight to the sand mound stuff and show you how quick it is to input the data into these spreadsheets. So here we go. Okay, hold harmless agreement. All right, I'm familiar with that, so I say yes. Okay, now here's something that was not on the previous spreadsheet. This is what I'm calling spreadsheet suitability. Basically, there are a certain number of items here that you need to make sure that the design meets before you apply the spreadsheet. So we see here that I'm saying that the laterals have to be identical in size, diameter, length, hole diameter, and have no bend fittings, meaning the laterals don't bend in the middle of the network. Actually, if they do bend in the middle, it's not going to make a huge deal, but it won't be 100% precise. And really, I was shooting for precision with this spreadsheet. So most designs are identical in size, diameter, length, and hole diameter, but sometimes they're not. So you need to check that. The actual inner diameter of the pipe is assumed to be the nominal pipe diameter. This is a difference between the Indiana Code methodology and the St. Joseph County methodology. We buy pipe based on the nominal diameter, 2-inch, 3-inch, 4-inch, whatever. But the actual inner diameter of a pipe is not actually 2-inch, 3-inch, 4-inch. It's something different. In some cases it's smaller, in some cases it's larger. And the St. Joseph County spreadsheet accounts for that, for the various pipe types. And it varies based on pipe type. So that explains it on a PDF that we created to talk about some of the differences between those two methodologies. The effluent in the system is downstream of a septic tank, not raw, unsettled sewage. Meaning that you're dealing with effluent. You're not dealing with solids in your fluent, in your sewage. If you're dealing with solids, it changes the properties of the actual fluid, and therefore it changes the hydraulics of the system. The laterals are at the same elevation. They're level, and they have more than 5 perforations per lateral, or 5 holes per lateral. So this is very standard too. They need to be level. And so we're not talking about stair step or 2 separate mound systems that are at different elevations. They have to be at the same elevation. And you agree to calculate friction in the manifold per Indiana Code 6-8.3 methodology. So Indiana Code methodology ignores the friction loss in the laterals, which is a significant amount of friction loss, and that's why the St. Joseph County spreadsheet accounts for that. However, as I said before, that the two methodologies, the St. Joe County methodology and the Indiana Code methodology, they still produce pretty similar results. So, okay. Do the conditions listed above describe the system? Yes. Okay, and here's some brief instructions. There's another one in there describing the inline residual pressure head, and I went over that in the first video, so I'm not going to cover that here. So let's go to the next page. So we're going to go to Emmaus again, and permit number. Okay, so in this situation, they chose a Zoller. As you can see in our county, that's the most popular pump. We are not endorsing any pump in our county. That's just happened to be the most popular one. Number of bedrooms, you can see that this input is up higher than on the flood dose spreadsheet. So it's 3. Soil loading rate. So this will be given by specifications from a county, or you can use the table 5 from the Indiana Code. The sloping area, you click on the drop-down arrow, you have 2 options. In this case, it's that option. Okay, so then here's some new input that we didn't have before. The aggregate bed dimensions and the basal area dimensions. So ag bed area for this situation was 375, the width was 5, and the length is 75. The basal area was 1575, 21, and 75. The force main was a 3-inch force main. And as you can see, all these drop-down arrows, they're all restricted to code requirement. So the code doesn't allow for a force main less than 1.5 inches or greater than 4. So that's why you have those options there. If it's outside of those options, it's not code compliant. Manifold, same thing. With the code, you only have the options that are available in the code. This is the the manifold length was actually only 3 foot, and the position, it's either center or end, and those are pretty self-explanatory. But let's say you're wondering, what does center or end really mean? You go to the help page, go to item number 3, manifold position, and you have some nice little diagrams here, compliments of the Minnesota Septic Professional Manual. Definitely a manual I recommend, one of the best out there. Okay, and then lateral spacing along manifold. So this is along the center manifold or the end manifold, the spacing of the laterals, so how many feet between them. In this case, it's 3. The lateral diameter, that's 1 foot or 1.25 inches. And then we have here the lateral length, and then the number of laterals. And notice when you input all that data in the tan cells that it populates and tells you exactly the total number of holes. This is a great little feature too, just in and of itself, because a lot of times it gets confusing with the placement of the holes and the hole in the end cap and how many do you really have. So this spreadsheet took me quite a while to write the code to do that, but let's say you're curious as to how it actually calculates that. Here's some examples in the help page. You can see that it always includes the end cap hole, and that it doesn't include more holes. It doesn't calculate more holes than half of the spacing at the end. So yeah, that's a nice little feature. Vertical length of force main, we went over that in the last example. Highest elevation of the force main. Again, you can use a datum, or again, it goes back to the dose tank. In this case, the designer did an average gallons per foot, and that was 269. And again, he had the pump off. So again, both of these two examples, the contractors like to use a benchmark at elevation 100, and everything beneath is everything beneath the ground at that benchmark is less than 100. Okay, so as far as the fittings go, he had some elbows that are just standard elbows. I'm sorry, he had 3. And then he had a check valve. So here I'm using the state code fitting values, and again, as I said earlier, it assumes that the fitting is the same size as the force main. So the force main is 3 inches, so these fittings are 3 inches. So if you went to the table, you would see that the equivalent length per fitting corresponds with that, and the total fitting loss is the summation of 3 11.1s plus a 25.5, so that gives you 58.8. We see the operating point here. We see that the pump curve looks straight, it doesn't look wavy, and the R² value is 1, so it's a perfect fit. And we can see here that the operating point is listed as 84 gallons per minute at 13.5 roughly feet of head, with an inline residual head of 4.8. So here's an example where the designer submitted something, actually, if I recall correctly, he submitted something where the gallons per minute was down here, and he had 3 foot of head. But as we can see, when you actually find the operating point, you see that the inline residual head goes from 3 to 4.8 feet of head. So it has a lot more pressure. But, let me just explain this too. This is different from the flood dose. It actually splits out your total system head at 84 gallons per minute. You have 6.4 foot of elevation head. Excuse me. You have 1.9 foot of friction loss in the force main, 0.4 foot of friction loss in manifold, 4.8 of inline residual head. And these are calculated the way the Indiana code recommends them calculated. Here's some equations if you want to be super nerdy and put in the flow rate, raised to the power 1.85 times that, plus this, plus, and do all that math yourself. And that's how you get the total head at 3.5 feet. So that's just an analysis for kicks, because I know that a lot of designers will submit the total head, and you can check that then. What exactly is a system head? Let me compare what I have in this spreadsheet versus what they submitted to me. And how much friction loss is in the force main? Is it 1.9 feet of head versus what they submitted? How much inline residual head versus what they submitted? It's quite a bit more. And then it goes through all of these checks. So we see here that they meet every single check. All of them are a go. And I'm not going to go into detail with all of these checks. They're listed in the help tab. So you just have to go to that item number and you'll look at all of them. I included all of the ag bed and basal area calcs because they're somewhat complicated and cumbersome. It'd be easy to throw them in the spreadsheet as opposed to checking those all the time, every pump submission. But also because the length of laterals changes the ag bed size and the basal area size, and the length of laterals and the number of holes correspond to or have an impact on the pump hydraulics. So all of these really are tied together. That's why they're in the spreadsheet. But we see that the code requires the inline residual head to be 3 feet of head. It's actually 4.8 feet of head. So a tip, if you want to change that, you can increase the number of holes, or you can decrease the operating flow rate. So, however, let's go to the help tab and see what it says, just for more thought on the matter. And it says here that in practice, ISDH personnel reject values less than 3 feet, but allow values larger than 3 feet. So if you want to follow suit with what they're doing, you could accept this and say that it's good. Okay. And also goes through and does quite a bit of design checks. The lateral diameter, it's saying it should be greater than 1.5 inches. So perhaps they need to consider changing the flow length, the lateral length or the operating flow rate. However, that's not a code requirement. That's just a general engineering check. These are based, the manifold diameter and the lateral diameter are based on procedures that Richard Otis developed at the University of Wisconsin, and where he said basically 10% of the loss of inline residual head can occur within a manifold or a lateral. And so therefore this spreadsheet says, takes that principle, turns it into the actual the lateral diameters that would produce that loss of friction head. Okay, it may sound kind of confusing there, but it really does all the math for us. So again, we see here that in this situation, it goes through and checks very quickly all of these checks with just very little time and input. So with that, these two examples, it gives you a taste of what occurs in these spreadsheets, the power of the spreadsheets, what you can do with them. And I hope that if you have any questions, take a look at the Help tab. It is very detailed, and we'll answer all of your questions. For anything else, Alice Quinn has offered her expertise to ask questions, but like I said, the Help tab has quite a bit of information in it, so really take a look at that. And I hope you enjoy the spreadsheets, and thanks for watching.